We try to have about half an hour to 40 minutes lecture. After that, we will solve some problem. Hope we have done your homework.
Teacher.
Yeah. Anything?
Hello.
Yeah.
No, can do half an hour only. Today, tomorrow I do 1.5. I can.
Don't want to change like that.
No, I feel very tired. I never sleep properly yesterday.
I don't want. No, I don't want to do that way. We come for 1 hour, we come for an hour. You don't want, you tell me earlier. If not suitable time, you have to decide earlier, not last minute like that.
Okay.
How to teach like that, half an hour. Just 1 hour, after that you go and sleep lah. What is happening? Okay. System in simple harmonic motion. Make sure you choose a day where you are not tired. Don't choose a day and then give me an excuse that you want to cancel the class or 1/2 an hour. There's no such thing. What type of class are you having? Okay, page 13 to 20. Right? Simple harmonic motion for small displacement in vacuum. Small displacement of 10 degree, less than 10 degree, and the period is given by 2 pi square root of L over G. L is the length of the pendulum. G is acceleration due to gravity. And 13, mass oscillating on a spring at a fixed end. Right? One end of the spring is attached. The other one is attached to a mass. So the period of oscillation is T is 2 pi M square root M over K. Right? You can use this one. The condition is that displacement is less than extension. Okay, so as far as the syllabus is concerned, these are the two that we will be deriving. But of course, they can also apply it to cases like this one that we have derived for you. Come out in your partial paper. Or case of one spring. Right? Instead of 2 springs, you can have 1 spring. Okay, let's go to example of simple pendulum. We are going to derive this equation. L is the length from the support there to the center there. Then natural frequency is F0, 1 over T. Right? We call it natural frequency because it's the frequency of oscillation of the pendulum. Right? Displace it, you can time it. Find the period and then find the frequency. And this angle is theta. So if you take this triangle, okay, you will find that this is your L, that's your X, right? That's your X. Rest position, this is the rest position, right? 2 is the rest position or equilibrium position when the pendulum is at rest, when it's not moving. And then when we lift it up, right? Or we displace it to an angle of 10 degrees, right? Remember 10 degrees is a small angle, and then it will oscillate from 3 to 2, 1, 2, and back to 3, and then carry on oscillating. Right? If the angle is 10 degrees, then this small arc there looks more like a straight line. That's the reason why we make it small. Or at the same time, we can also use the approximation. Right? Theta in radian equals to sine theta. Right? In this case, it's x over L. Okay, x over L. Or you can think of a circle. This is a radius. The circle there, you still get the same formula. Right? Your arc length there is theta, that angle there, theta, that is your arc length there, times L. right? Theta times L. Either way. Okay, we are going to do that. Show that for small angular displacement of less than 10 degrees of the form of simple pendulum, show that the motion is simple harmonic. That's the first step. After that, you want to find the period is equal to that. Right? Derivation. We have displaced the bob. That's the rest position. Displace it to position B. The angle is theta. This is also theta. Right? Alternate angle. That is your string. Okay, when the bob is displaced to position B, the forces acting on the bob is the weight. Right? The weight will be pulling it down vertically downwards, W. That's your tension the string. Right? That's your displacement X from the rest position. So we can redraw that. That's your tension. And then we can resolve the weight into its component, two perpendicular component, X and Y. D. Then we have, remember this is also theta. This angle is also theta. So this is far away from the angle. So it's W sine theta, it's W cos theta. The resultant force F, right? So that force there, that D, is balanced by W cos theta. Right? Remember when the cos theta is small, this is like horizontal, normal arc already. And then this is also like horizontal. That resultant force is horizontal. Okay, so that is where we have gone over just now. You can think of it as a circle. That is your radius R. And this arc length is just your S R theta, or X equals to L theta. Right? Theta is X over L, or you can use small angle. Theta equals sine theta, same thing, same idea. Okay, let's carry on with the derivation. Right? These two balance. So this is more like horizontal. That's the resultant force. Right? Remember, resultant force of Newton's second law is equal to MA. You put a negative sign there because your resultant force is to the left. Okay, just imagine this is horizontal, right? Because the angle is small. Resultant is to the left, the displacement is to the right. Right? As a displacement to the right. So we take the right as positive. That's the reason why we have a negative sign there. So M and M can cancel off. So we have A equals to minus G sine theta. Right? Replace the sine theta. Okay, replace the sine theta with X over L. So we got A minus G L X there. Right? G, remember G over L is a constant. So it shows us that your A is proportional to minus X. So this is what is required. Show that the motion is simple harmonic motion. Right? As long as A is proportional to X and is negative. Right? That means A is proportional to the displacement. At the same time, A and X are in opposite direction. That's the purpose of the negative sign. So we have shown that it's simple harmonic motion. Now we are going to derive the period. Okay, that's what we have shown, the equation. Compare with the definition. That's the definition for simple harmonic motion. A is proportional to X. That's your angular frequency. So angular frequency equals to GL. Okay, so square root that, we get our square root G over L. Then period is 2 pi over omega. So we can replace omega here. So it becomes 2 pi square root L over G. Any questions so far? Anything not clear? Yep. Any comment? Anything?
No, nothing.
Okay, let's carry on then. Okay, let's go to the spring. Review your SPM work. There's your spring, the natural length there, without any mass there. I can put a pointer there. Can add mass there. And as you add each mass, we can measure the extension. There's your extension. There's your mass there. You can add another mass. Right? Same mass. So this is W, this is M, this will be 2M or 2W if you think of weight. So the force is pulling it up. This is the force by the spring, right? Equals to the weight. Then we can plot a graph of force against extension. Right? Force is the stretching force or the applied force equals to mg. X is the, sorry, it should be not X, it should be E. We use symbol E. Okay, that's your new length. There's a reference point there. There's the original length. So we subtract, get E. K is a spring constant. So F is equal to KE. So if we plot a graph, that's how we do it there in the lab there. If we plot a graph, there's our graph there. Right? We are interested in the region, this region, where the spring obey Hooke's law. That means the straight line region. Not interested in that part there. Right? So only in this straight line region is the force proportional to the extension. Right? Force proportional to extension. Sorry, I keep on using X. E is the extension. And then the energy stored.
Yes, sir.
Right? That's the energy stored, half KE squared. Okay, if no problem, let's carry on. Right? Remember, that's our original length without any load there. Page 17. Right? There's original length there, L unstretched. Then we add a mass there. It is stretched. The extension is E. The force acting is the tension of the spring. And then mg. Right? This is called the rest position, where it's not vibrating. So the tension by the spring equals to weight of the mass, M. So T0 equals to mg. Okay, so that is the, we can take that as our reference point, the top of the mass, 0. And then we pull it down by displacement x. Right? Mass is displaced by displacement x downwards. X is less than E. That's your E. X is less than E because our X has to vibrate up to here. It cannot go over there. Over there is normal tension. We cannot use that normal simple harmonic motion here. So your X has to be less than E so it can vibrate less than that distance there. Right? Just that distance. So the force acting, the tension there is now T1. Right? Equals to, right? Your extension now is E plus X. So it's K X plus E. Okay. Any comment?
No, so far nothing.
Okay. Right?
Oh, elongation is dependent on elongation. The elongation has to be short, right?
Elongation depends on the mass.
Yeah. Elongation
No.
is also directly proportional to period, right?
No, we will see. We will derive that. No, where got? Where got?
My teacher said lah.
That one is for the, oh yeah, for the spring, yes. Anyway, we will see, we will see. I don't think it's directly proportional. There's a square root sign there. Okay, we got T1, we got T0, and we want to find the Right? When the mass is released at this point there, remember we pull it down from the rest position, we pull it down. So now there's going to be a resultant force upwards. Right? The resultant force, put an arrow that shows it's going upwards there. So the resultant force is T1 minus T0. Okay, so subtract K into X plus E minus KE, you got KX, right? That one there minus that, you got KX. Okay. So the resultant force is the one that will cause it to oscillate up and down. Right? And that resultant force depends on the X there. So the object will move up from A to O to B, back to O, back to A. Okay, so now we have to look carefully. We are going to consider it's a vector. So resultant force equals to Kx. I apply Newton's second law, F equals to ma. Right? Remember the resultant force is pulling upwards there. Displacement is from the rest position. This is the rest position. Right? Resultant force is pulling it up. Rest position is there. The displacement is downwards there. We are taking downwards as positive. We have to add a negative sign there to show that this, because acceleration and displacements are vectors. Then take the m down. We got our minus km x. Right? K spring constant is K and m is constant. So we have shown that A is proportional to X and there's a negative sign there. Right? We show that acceleration is proportional to displacement and acceleration is always opposite to displacement. So we have shown that the spring is vibrating in simple harmonic motion. Okay, now we are going to find the period of oscillation. As usual, we compare with our definition. That's our definition. So now this omega square equals to km. And you square root that. You want 1 over omega. So this becomes inverted. M over k. Right? Period is 2 pi over omega. So replace that 1 over omega there. We got our 2 pi over mk. Okay, any problem so far?
No.
Right? So we can see that the period is independent of g. Right? So that's why in space where there's no gravity, where the astronaut circle around the Earth, there's weightlessness. To measure, we can use this one. We just displace the mass, and then we can find the period because the period depends on the mass of the oscillating object. Right? That's why we measure in space, measure mass in space. Right? We first have to calibrate it first. Calibrate different mass, what is the period? And then in space there, you want to measure the mass of anything, we just find the period and then use a calibration graph to calculate, or we can calculate to get the mass of. Right? Alternative formula. Remember our formula, that one there. Our T0 is mg. Mg equals to ke for this part there. Right? Take the e down, take the k down for mk, and then take the g down, e over g. Okay, replace that. Square root of e over g. Okay, not proportional. Square root t is proportional to square root of e. Okay, any problem? Any comment?
Nope.
Okay, let's carry on then. Okay, so we have more or less completed this part. These are all the formulas that you need to know how to use. Right? These are the 2 extra there. Okay, let's go to damped oscillation. Right? In free oscillation, no resistive force. That means the object is oscillating to and fro in vacuum. Right? No resistive force. That means no friction, no air resistance to oppose the motion. In damped oscillation, we let the pendulum oscillate in air. That's called damped oscillation. Air resistance is the resistive force. It opposes the motion, so the amplitude of the oscillation decreases. Right? In forced oscillation, right, as the name called force, we force it to oscillate by applying a periodic driving force to cause a particle to oscillate. Right? In this case, the amplitude can be constant because the force, the periodic driving force is the one that supplies the energy. Okay, so that's what we require for your syllabus. Damped oscillation, describe changes in amplitude and energy for the damped oscillating system, distinguish between damped, critical damping, and over damping. When a simple pendulum oscillates in air for some time, what do you observe in terms of amplitude? Okay, what do you observe in terms of amplitude? Yeah, what do you observe? Simple pendulum where it's oscillating after a while. Why so tired?
Yes, Chair.
What happened to the amplitude? Yeah. You have been doing experiment in class in your STPM. What happened to amplitude?
The amplitude increases and decreases.
Where got amplitude increases and decreases? Amplitude is the maximum displacement from the rest position. So what do you observe about the amplitude? It goes like that. That's the rest position. It goes that way, come back, go back there, there. And you observe like that. Yeah, what happened to amplitude?
It moves from left to right constantly.
No, you are not paying attention in class. Amplitude decreases with time. As it oscillates to and fro, amplitude becomes smaller and smaller until it stops completely. That's called damping. Right? So if amplitude decreases, then the total mechanical energy also decreases. Right? The energy work done against resistive force, the air resistance, so that's converted to heat. Right? So if the total, remember the total mechanical energy is proportional to amplitude square. So if the amplitude decreases, the total energy also decreases. Important. Right? M and omega square is constant. There's a change for the particular system. For the mass you use. Okay. E is proportional to amplitude square. Right? So what is damping? Damping is a continuous or gradual loss of energy from the system. You can describe it this way. Continue to lose energy, the system, until it stops, or the amplitude decreases as the force is always opposing the motion. Right? Amplitude decreases because there's a force opposing the oscillation. In free oscillation, there's no air resistance. Total energy is constant. Remember when we say total energy, it's the total energy of the system. Right? So in this case, free oscillation, the kinetic convert to potential, potential to kinetic. That's all. But in damped oscillation, as a mass oscillates, air resistance opposes motion. So there is going to be work done against air resistance, and that work done is lost as heat. So now it means that the total energy now will decrease. Right? Total mechanical energy decreases. Type of damping. We look at right? Light damping or under damping. Right? That's how we see simple pendulum oscillating to and fro, amplitude start to decreases. Right? Decrease slowly, amplitude decreases gradually. Total mechanical energy decreases. See, we are repeating it ourselves. Period of oscillation remain constant. Period doesn't change. There's a period. There's a zero. There's a period. Okay, and if you plot the amplitude against time, then that's what you see. This curve there, exponential curve. Okay, not straight line, exponential. Right? In terms of energy, if it's simple motion, remember it's a straight line. Right? If it's a damped oscillation, total energy decreases. Right? We are just repeating where there's a energy loss is used to do work against friction. Right? Amplitude of oscillation decreases gradually. Okay, let's go to critical damping. Right? These are free oscillation. Amplitude is constant, go to and fro. Right? But in critical damping, object is displaced when released, return to the equilibrium position. There. That's all. It doesn't oscillate. It just comes to rest here, shortest time, without overshooting. That means it doesn't go to the negative part there. No oscillation. Right? The time is the shortest, a quarter of the period. Then the other one is heavy damping or over damp. Right? It's a displacement. That's your time. So that it starts to decrease. Take a long time to go back to zero. Right? So here the oscillate object is placed in the viscous medium. That means a lot of friction, a lot of resistance to motion. Right? Like you can oscillate your spring, your mass there on a spring or simple pendulum in glycerin or oil. Okay, we are stopping in a short time. Then we will start a new Zoom. No oscillation occur. Your object displaced takes a long time to return to rest position. No useful application. Right? Critical damping got useful application. Heavy damping, no point. No useful application. Right? In lab, we can do this experiment. These are your string. Right? This is your meter. This can be a piece of wood. And then that you can change this cut. Right? Change the area to increase the damping or decrease the damping. Right? The bigger the area of the cut, the greater is the damping. Okay. So critical damping is useful. Right? Used in moving coil meter. Right? We want the pointer to swing to the reading you want to read. Oscillate a bit and then come and stop. Right? We don't want it to oscillate to and fro because it takes too long time for it to stop and then there's no use if it's so we critically damage or suspension of a car. This is a suspension of a car. Okay, a good ride. During the 60s, there the car has what I call that light damping. Right? If you have the old fashioned car, so you go into a rough road or bumpy road, it will go up and down. Okay, whereas a modern car is not that bad. You go to a bump, it will oscillate for a while and then it come down. Right? It oscillate and come down, more comfortable. Okay, so that's the car suspension. Okay, so that's your moving coil galvanometer. So we have completed that. We only got one more part. We will do it tomorrow. So if you haven't done your homework, I will stop here and then you can try to do some work or have a drink. If you're tired, have a drink. Any question you want to ask?
No, so you're gonna send a meeting in 10 minutes, Acha.
5 minutes. 5 minutes.
Oh, okay.
We will spend another half an hour doing the exercise. We don't want to delay already. You want delaying you. If you are tired, let me know next time. Choose a day that you are not tired. If not, we will have to have Saturday 2 hours already next time.
Okay.
Okay, so I will stop here.